The Mars Rover missions aim to research the history, climate, and geology of Mars as a precursor to human exploration. The rover must be able to traverse unknown hazardous terrain to succeed in its scientific endeavours. The difficulties associated with the challenging Martian terrain have led to the mission-ending entrapment of the Spirit rover in 2009 and significant wheel damage to the Curiosity rover in 2017. A solution is required for the safe exploration of areas of scientific intrigue on Mars. This led to the following research question. How can deep learning be employed for terrain classification as a component of traversability analysis on a Mars rover? The proposed solution consists of an RGBD camera, which obtains colour and depth images of the surrounding terrain. A trained CNN performs semantic segmentation on the colour image, yielding pixel-wise class labels identifying each type of terrain. A height map is constructed by the deprojection of the depth image. Based on the rover kinematics, 7 possible motion arcs are defined. The traversability of each path is assessed as a function of the terrain predictions, relative terrain height, a local goal, and the energy expenditure of a given steering angle. The path with the highest traversability is identified and executed in simulation. Previous rover missions employ the Gestalt navigation system, which utilizes stereo vision to assign discretized cells with a traversability score based on topographic features. Deep learning for terrain classification could extend on Gestalt to provide an additional method of risk assessment. The SORPY rover is utilized to model the layout, proportion, and rocker bogie suspension of the Curiosity and Perseverance rovers. Based on the Mars Exploration rover parameters, an obstacle height limit of 12 cm, yielding a maximum pitch of 25 degrees, is defined. The rover motion is constrained by the Ackermann geometry, accounting for the difference in steering angle and velocity for each wheel given a common instantaneous center of rotation, or ICR. 7 candidate arcs are defined in a 1 meter square region of interest in front of the rover. The angle defined by the arc and the rover body velocity are solved. Then, the individual wheel velocity and steering angles are solved and utilized as the input parameters in simulation. The coordinate reference frames are then considered. The pixel in the image frame is converted to the camera frame using the intrinsic camera parameters. A transformation matrix then defines the translation and rotation between frames. The camera, tilt, pan, rover body, and local ground reference frames are then compounded, yielding the image point in the 3D local ground coordinates, defined with respect to the rover body. The traversability estimation algorithm is implemented in Python with ROS for simulated rover motion in Gazebo. A 2D height map is constructed by applying the coordinate transforms discussed on the depth image data corresponding to the colour image shown. The known camera height and tilt enable the calculation of the 3D coordinates of each point within the 1 meter square region of interest. Semantic segmentation, as an application of deep learning, classifies each pixel in an image, chosen over alternative deep learning methods such as object detection and instant segmentation, as we require the terrain classification of irregular shape features at a specific location. Some examples of the predictions of the trained network on images from the Mars Lab and the terrestrial testing site are shown. Each pixel is classified as either large rocks, small rocks, compact dirt, objects, or walls of the Mars Lab. The Museum of Arts and Applied Sciences Mars Lab yields an area of simulated Martian terrain, created with an emphasis on scientific accuracy. Colour and depth images were obtained with the RealSense D435 RGBD camera at both the Mars Lab and an outdoor testing site, with a resolution of 640 by 480 pixels. The RGB images were labelled using the MATLAB image labeler, producing a raw dataset of 153 images and corresponding labels. Each image and label was then cropped into two 480 by 480 segments and resized to 224 by 224. The dataset is split into 70% training, 25% validation, and 5% testing data. Due to the relatively small dataset, image augmentation was implemented to avoid overfitting by introducing variation in brightness, contrast, saturation, scale, reflection, and rotation. A convolutional neural network was trained in Google Colaboratory. Several model architectures and loss functions were compared, with the final model utilizing a VGG16 base and SegNet segmentation model, implemented with categorical focal dice loss to address the imbalanced nature of the dataset. SegNet adopts a symmetrical encoder-decoder framework. The model is trained over 50 epochs, yielding a training accuracy of 93.95, a validation accuracy of 85.54, an F1 score of 83.53, and an intersection over union of 73.7. The summarized confusion matrix of the trained model on the testing dataset is shown, with the strength of the diagonals indicating its success in identifying compact dirt, large rocks, and small rocks as required. For each waypoint along the path, the cost defined by the measures of class, height, proximity to a local goal, and the steering angle is incorporated into the cumulative traversability score. The rover display shows the input image, segmentation output, height map, and the path selected. The selected path is then executed by the rover in a gazebo simulation, verifying the successful implementation of the traversability estimation algorithm. This thesis contributes an implementation of deep learning for terrain classification, a traversability estimation algorithm for extended risk assessment, and path planning and control of a Mars rover exhibited in simulation. This work paves the way for future extensions, some of which could include extending the dataset for improved classification, building on the measures of traversability, and employing the traversability estimation algorithm on a physical rover. Thank you for listening.